Hello everybody and welcome to Thermal Physics Lesson 3. Now in the last video we looked at specific heat capacity and we had the equation delta Q is equal to mc delta T. And just to remind you, delta Q was change in heat and delta T over here was change in temperature. In the middle then, M was mass, and the key part of that then was C, which was the specific heat capacity, which we defined in the last video. And now just to remind you of units, change in heat, remember, is a measure of energy and is therefore joules. Mass is in kilograms, change in temperature is in Kelvin, and therefore the specific heat capacity unit is joules per kilogram per Kelvin. Now obviously that was very heavy on the theory from the specific heat capacity point of view, and what we're going to do now is you're going to bring it forward and have a look at sort of translating that and looking at how it would work from a practical point of view. Now if we were going to take a substance and we were going to heat it up, so let's say we just had very simply a beaker of water over a Bunsen burner or something like that, and we had a constant amount of energy going into, in other words the power input was a constant, and we were to measure that temperature as a function of time, then what we would see on the screen is the graph that we would get out of that. Now actually this graph would be taking it all the way from a solid all the way through to a gas, all the way through to a vapour, obviously in the case of water at the far end. So if we have a look at this graph in a little bit more detail, hopefully what we can see is that in that portion A to B on the graph, obviously we've got a solid at that point, and we're heating the solid up. From C to D we've got a liquid, and from E to F we have a gas. Now, as I said before, if we assume that we have a constant power, okay, so in other words, we've got a constant energy input, then from the graph, we're going to be able to work out quite a lot about the substance. So let's have a look at what the gradient of the graph represents. Well, the gradient is temperature on the y-axis, and obviously we've got time on the x-axis. Remember, of course, that when we're talking about power, that power is the rate of energy transfer, so it's energy over time. If we take the specific heat capacity equation then, so delta Q is equal to mc delta T, and what I'm going to do is I'm going to divide both sides of this equation by time. So over here I'm going to divide by time, and over here I'm going to divide by time as well, being a little bit tactical about on the right hand side where I put that delta T. Well, of course, when we then translate this bit here, the delta Q by delta T, that will equal the power input, and we can see that the delta capital T over delta lowercase t we've already shown is the gradient of the graph. What we end up with then, power is mc multiplied by the gradient, or in other words the gradient of the graph will be the power divided by m times C, the mass of the substance divided by the specific heat capacity. Now, of course, for power, we can look at this in a couple of ways. If you're using some kind of immersion heater or some kind of electric heater, then obviously the power can be calculated from the current and the potential difference, so we can substitute IV into that, or of course if you've got a calorimeter or something along those lines, a joule meter, you can tell from those devices how much energy is being put into the substance. So there are all kinds of different ways of working out the power from that, but of course the whole idea of doing an experiment such as this would be to calculate the specific heat capacity. Now, of course, all of that is well and good for the bits of this graph that are sloped. So on the last slide, we covered A to B nicely, we covered C to D nicely, and we covered E to F nicely. But of course, what we didn't discuss are these two bits here, B to C and D to E. Now, hopefully, straight away, what we can see is that these points here are when we have a change of state. So this temperature here on the graph would be the melting point, and this one up here would be the boiling point. Now, of course, the reason why the graph changes at those points, instead of being obviously a slope, it goes to being flat, it sort of plateaus at that point. We're still putting energy into this substance, we're still putting energy into the system. But of course, that energy in the system is being used in slightly different ways. When we're heating, so at these points here, the energy goes to increasing the kinetic energy of the molecules in the substance. Whereas when we get to these two changes of state, to the melting point and the boiling point, the energy now is going to breaking the bonds between the molecules in order for them to change state. But of course, because at those points now the energy isn't going to increase in the kinetic energy of the molecules, we don't get a temperature change. So we have to note at that point that there is no change in temperature. Now, of course, that causes us, from an equation point of view at least, a little bit of a problem, because of course the specific heat capacity equation says delta Q is equal to MC delta T. Well, of course, at the boiling point and at the melting point, what we're saying is that delta T at those points, okay, so at that point and at that point, is equal to 0. We're still putting energy into the system, so delta Q certainly isn't 0 at that point. Well, the mass isn't 0, the specific heat capacity is not 0, but suddenly we're saying that delta T is 0. In other words, that equation must therefore no longer apply when we're at the change in state. So what we need to do now is we need to have a look and we need to define a different term, and it comes down to latent heat, and there on the screen you can see the definition. So the latent heat is the energy required to completely change the state of 1 kilogram of a substance with no change in temperature. Now again, the equation to cope with this, then we still have delta Q. We've still got the mass, but now we use just L for latent heat. Obviously in this one, delta Q still means change in heat, and M still means the mass with the same units. So delta Q has the unit of joules, M has the unit of kilograms, and the unit of latent heat is therefore joules per kilogram. Now, while obviously if we go back to specific heat capacity, we've got different specific heat capacities depending on the state of matter. Well, exactly the same happens with latent heat, and we have two different latent heats depending on whether we're at the solid to liquid change of state or the liquid to gas change of state. Now, these two are known as, firstly, the latent heat of fusion, which sometimes is written as an L with a subscript F, and that one is when we have melting, so we have the solid to liquid change of state. For liquid to gas, we have the latent heat again, but this time it is of vaporisation, and we use an L with a subscript V, and that is for liquid to gas. So when we bring all of this back together with the heating curve then, so we've already said that here A to B, here C to D, and here E to F is when we are heating the various states of matter. So in those three areas on the graph, we're going to apply the specific heat capacity equation. Delta Q is equal to MC delta T. In the two flat bits of B to C and D to E is where we have changing state, and therefore we need to apply the latent heat equation. Delta Q is equal to ML. And obviously for all five portions of these graphs, we're going to need different constants for specific heat capacity or latent heat. So obviously here we're going to need the specific heat capacity of the solid form, here we'll need the specific heat capacity of the liquid form, and here we'll need the specific heat capacity of the gas form. In this section here we'll need the latent heat of fusion, and here we're going to need the latent heat of vaporisation. Now, of course, then, because we're looking at loads of different values, we end up having to have loads of different data tables and all that kind of stuff for substances and whatnot. Now, there is obviously no way that you'll ever need to remember all of these different values when it comes to doing this properly or doing it in an exam or anything like that. You'll either need to calculate them or you'll be given them. In reality, what we tend to do is obviously just look them up. If we want to know a value, we'll either just go online or grab a data book and have a look through all of these values. So let me just give you all of the data that we care about for water then. So we saw it in the last video as well. The specific heat capacity for solids, so for ice, is 2100 joules per kilogram per Kelvin, and then the latent heat of fusion to go from a solid to a liquid is 334 kilojoules per kilogram. Then obviously for a liquid, we saw again in the last video, we've got 4,200 joules per kilogram per Kelvin. Latent heat of vaporisation is 2,260 kilojoules per kilogram. And then finally, for a gas, again, just bringing that forward from the last video, we've got 2,000 joules per kilogram per Kelvin. Now, as I said, guys, there's absolutely no reason for you to know all of those. They'll either be given to you or you'll have to work them out. The only one that you do have to remember is for liquid, so for the specific capacity for liquid water, which is 4,200 joules per kilogram per Kelvin. So you do have to remember that one. Now, knowing full well that it's really boring just to see me put a load of numbers on the screen, there is obviously a point to me doing this. We can see, at least from the specific heat capacity point of view, we're dealing with the same kind of order of magnitude. We're dealing with joules per kilogram per Kelvin, and obviously it is in the thousands there, but we kind of get the point. What we see though from the latent heat is that suddenly we're dealing with kilojoules. Now, the point of me showing you that is to illustrate to you that it takes far more energy to change state than it does to simply heat up the substance in the first place. So you can see that just to boil water to go from liquid to a gas, we're talking about 2,200 kilojoules per kilogram rather than changing just 1 degree or 1 Kelvin of 4,200 joules. We've gone from joules up to kilojoules, and therefore far more energy is required in that change of state than just in the heating process in the first place. Finally then, before we move on to the question for this video, and just to round everything off, I know that obviously in this video and in the last video I've really been focusing on everything heating up, so energy being put into the substance, but of course it all works the other way around. In other words, if we are taking energy out of the substance, if energy is being released and therefore the substance is cooling down, all of this works perfectly well in reverse, because don't forget we have delta Q is obviously MC delta T, and delta Q is equal to ML, and obviously with the deltas there we can have positive or negative for both of them, so it works both ways. So obviously if delta Q is positive, then that tells us that we are heating, and if delta Q is negative, then we are cooling. Here then is your question for this video. How much energy is required to transform 700 grams of ice at minus 20 degrees Celsius into water at 65 degrees Celsius? As usual, pause the video at this point, go and have a go at it and come back when you've got an answer. Now, with this kind of question, unfortunately, we're just going to do a little bit of brute force and ignorance, really, and we've got to split it down into 3 separate calculations, 3 separate parts. So what we've got then is, obviously, we've got the ice bit first. That goes from minus 20 to 0. We then have the melting, and then we have to take the water from 0 degrees C all the way up to 65 degrees C. So for the ice then, obviously we need the specific heat capacity equation, so we need, let's just remind ourselves, delta Q is equal to MC delta T, and we need delta Q is equal to ML. So for the ice then, delta Q is equal to, mass is 0.7 of a kilogram. The specific heat capacity there is 2,100, and then if we're going to do it properly, the change in temperature, well, final is 0, and we're going to subtract from that minus 20. Now obviously what that translates into is plus 20, but again I'm just showing you the correct way of doing it. For the melting, well, delta Q, the mass again is 0.7 multiplied by the latent heat of fusion, which will be 334, and obviously because it's kilojoules per kilogram. We just need to times by not 10 to the minus 3. We need to multiply by 10 to the 3 with that. Then the water, delta Q is M, 0.7 times the specific heat capacity, 4200 multiplied by, and again, final is 65 minus initial is 0. For the ice then, when we plug that into the calculator, we end up with 29,400 joules. For the melting stage then, we end up with 233,800 joules, and I will just leave it as the full calculator answer for now. And then for the water bit, we end up with 191,100 joules. When we add those all together then for the total energy, what we end up with is 454,300 joules, and of course I'm not going to leave it as that. That's fine for the intermediate calculations, but I'll probably end up turning that into a total energy of 454 kilojoules. Now again, you can see from an illustrative purpose there, so we're taking ice at minus 20 all the way up to water at 65 degrees C, takes 454 kilojoules, and just over half of the energy required came in the melting of the ice into water. So again, that just shows you that it is a significant amount. It's the most of it there is the change of state. Far more energy again goes into the change of state than it does into the heating process. So to summarise then, in this video we first looked at heating curves, and we noted the difference between when we are changing temperature and applying the specific heat capacity equation, and when we have the change of state and we are applying the latent heat equation. So remember, if we are changing temperature, then we apply delta Q is equal to mc delta T, the specific heat capacity equation. But if we're changing states, then we apply the latent heat equation, delta Q is equal to mL. And of course L there stands for the latent heat. Definition at the bottom right, so the latent heat is the energy required to completely change the state of 1 kilogram of a substance with no change in temperature. And then finally we showed that there are two slightly different approaches to latent heat depending on exactly which change in state we are looking at, and LF, which is the latent heat of fusion, was for solid to liquid, and LV for latent heat of vaporisation was for liquid to gas. Finally, of course, we said that all of this does work both ways, so whether we're increasing temperature or changing state, going from solid to liquid, liquid to gas, or we could be going the other way around. In other words, we're cooling down, we're reducing temperature, we're going from gas back to liquid or liquid back to solid. All of these equations apply no matter whether we're increasing energy, increasing the heat, or whether we're energy being released and therefore cooling everything down. So that's it for this video. As usual, thanks for watching. I hope you've got something useful out of that, and I'll see you in the next video.